Hey guys, welcome back to the channel, and today we have the small signal analysis of the common drain. Now, important to note, this is a MOSFET. We've graduated from the BJT transistors and now we're onto the MOSFETs. So just on the screen right now, I'm showing the small signal equivalent model of the MOSFET, where we can clearly see that VGS, which will be the difference between the gate and the source, will be controlling the current source attached to the drain and the source. So what's important about this is that the current in ID and IS will be the same unless there's channel modulation. Then it's a little more complicated, and there's no current running through the gate. It's really important to note. And if there is no channel modulation in the question, which is highly unlikely, then simply all you have to do is just remove this resistance knot, the resistance outlined in blue. Also important to note, for an NMOS or a PMOS, it's the exact same circuit model. In the BJTs, we saw that the currents were flipped, but for the NMOS and PMOS, it remains the same. So in the first question, let's get this started. So always, we have to draw the circuit in the small signal domain. So we're given a bunch of the resistances right here, and we're asked to compute the voltage gain and input resistance. So in this case, once we draw the small signal domain, we'll be able to get a nice picture of how we can solve this question. So as always, when you're drawing the circuit in the small signal domain, you always want to draw the model first. I find that's the easiest way for me, and it just helps me get everything organized. So we know that the source is GMVGS. This is the voltage difference between the gate and the source, and we have the R0 resistance. So now that we have this, we can start adding the components. So whatever we have to the left of the MOSFET is always going to be the gate. Whatever is on the opposite side, so this side of the MOSFET, where there's only one component attached to that side, is going to be the gate. Now, whichever component has the arrow, this is going to be the source. And whichever one is on the side with the two components, but does not have the arrow going in or out of the MOSFET, it's going to be the drain. So that's how we can easily tell. And for AC analysis, it doesn't really matter, but to determine if it's an NMOS or a PMOS, the NMOS will have the arrow flowing outside of the MOSFET, but in a PMOS, the arrow will point into the MOSFET. So let's start by drawing this out. In the gate, we see we have a gate resistance, grounded, attached to a voltage source, Vin. Now, really important to note, just to remind you guys, how are we drawing the circuit? Well, we're short-circuiting the capacitors and deactivating all DC sources. So now in the source, we see that we have a DC current source. Now, how do we deactivate that? To remove current, we simply just open circuit it. And once we short circuit the capacitor, we're simply just left with RL, which is where the output voltage will be. And now in the drain, all we have is just one resistance, RD, and that'll be grounded. Now remember, all the resistances are given above. We have GM, which is a DC parameter, which you will have to solve for. Same with R0, but the DC analysis will be a separate video. I just want to cover the AC today. So this is our circuit in the small signal domain, and now we can start the computations. So now let's compute the voltage gain. I want to point out too, this is probably the hardest transistor there is. I know a lot of people that I knew struggled with this one, but there's so many ways to do this too, but I'm going to show you guys the way I think is the easiest. So first, what we're going to do is, really important to note, VGS equals VG minus VS. So from what we can see, we know VG is going to be the voltage right here. And that's simply going to be V in. So we know that VG equals V in. And now what would VS be? This would be VS right here. So VS is clearly going to be equal to V0, as we can see from the circuit. Now, what we can write from this is VGS equals V in minus V out. Alright, so that's something really important we have to note. Because VGS controls the current source, that's why we're finding this. Now, the easiest way I think to do this is to simply perform a KCL at this node. We'll call that VX or VD and VS. So we have two places where we can perform KCL, and let's see what this result gives us. So if we do KCL at node VD, we simply see that all of these currents are simply just going to flow downwards. So the current in the RD is going to be VD over RD. The current in the R0 resistance will be VD minus the voltage here, which is simply just VS. You see there's nothing dropping the current in this wire. So VD minus VS over R0 plus GM VGS is equal to 0. Now remember, we found a formula for VGS, so we can simply write this as VD over RD plus VD minus VS over R0 plus GM V in minus V0 equal to 0. So what we can get from this is we can find a formula or an equation for VD in terms of V in and V out. And VS would be V out. My bad, sorry about that. Why did we want to do this? Because for our other KCL equation, we see these will be the three currents in it. I labeled them in green there, and we see that the current going through R out is depending on VD, but we don't know what VD exactly is. So this is just a way of writing VD as a function of V in and V out. So once we factor out VD and move V out and V in to the other side, we simply are left with 1 over RD plus 1 over R0 equals GM V0 plus V0 over R0 minus GM V in. Now, simply all we have to do here is just plug in the numbers and find an equation for VD. So once we plug in the numbers, we see 1 over RD plus 1 over R0 is simply equal to 2.1 times 10 to the negative 4 equals, and we know GM was given earlier as 9 times 10 to the negative 4 V0 plus 1 times 10 to the negative 5 V0, because 1 over R0 is, remember, R0's given earlier as well, minus 9 times 10 to the negative 4 V in. Now, all we did was just plug in numbers that were given in the equation. So we can simply divide both sides by 2.1 times 10 to the negative 4, and we're just left with VD equals negative 4.29 V in plus 4.33 V out. So now that we have a formula for VD, we can now start the KCL. I'll remove this to get some space here. We can now start the KCL at node VS. So what we see here is we have two currents going into VS and a current leaving. So we can write this as GM VGS plus, remember, this is why we found VD, plus the current going through R0 would be VD minus V out over R out equals V out over RL. So now we can see, remember, VGS is equal to V in minus V out. So we have GM V in minus GM V out plus VD minus V out over R out equals V out over RL. Now we can simply plug in this VD into our equation here, and we'll be left with negative 4.29, or my bad. Once we plug that in, we'll be left with GM V in minus GM V out minus 4.29 V in over R naught minus 4 or plus 4.33 V out over R out minus V out over R out equals V out over RL. So now once we move all the V outs and V ins to their own respective side, we can see V in negative 4.29 over R naught plus 9 times 10 to the negative 4, which is GM, is equivalent to V out 1 over RL plus 9 times 10 to the negative 4, which is GM, minus 3.33 over R naught. Now we can simply just plug in 3,000 for RL and 100,000 for R out. And what we're left with is V in 8.571 times 10 to the negative 4 equals V out 1.2 times 10 to the negative 3. Now we might have skipped some steps, but I'm really not here to teach you algebra. So I'm assuming you guys all have very strong algebra skills. So once we divide both sides by V in and 1.2 times 10 to the negative 3, then what we're simply left with is 0.71 volts per volt. And this will be our voltage gain. Now, if you guys can do this, you guys can definitely do any other transistor voltage gain problem. This is by far definitely the hardest and the longest one. And now for the input resistance. Get this in here. Oh, my bad. Sorry about that. I don't know what's happening with this. Okay, let's get rid of this. Rewrite V in here. So for the input resistance, as always, we're essentially finding a Thevenin equivalent resistance. And we see here that V in is across this current voltage source right here. I circled it. So simply what we do, just like the transistor, we can either add a 1 volt voltage source or a 1 amp current source, and we can easily find the resistance from there. So in this case, I personally like to add the 1 amp current source, but it's really up to you. Now simply all we have to do is find the voltage across this current source. Now what's really important to note here is that the gate is not connected to the source or the drain. So this current, the 1 amp, is flowing through the entire gate here. So simply what we can write this as is VT equals IR. And what's really easy about this is the current's just equal to 1. So we know that VT equals RG. So therefore, the input resistance equals VT over I. And we know that I is equal to 1. So we can simply just write this as Rn equals Rg, which from earlier I believe was 3,000, 2,000 ohms. And that's our final input resistance. Thank you guys so much for watching. I really hope you guys learned something.